So today's topic is 8.2 transformations of logarithmic functions, found on pages 383 to 391 in your text. Curriculum outcome, we're dealing with 30.9, which is still talking about logarithms, which we need to demonstrate an understanding of logarithms, including evaluating logarithms, relating logarithms to exponents, deriving laws of logarithms, solving equations, and graphing. Our lesson objectives, there's 4 of them today: to learn the general form of a logarithmic function that is undergoing transformations; 2, to apply previous knowledge about transformations to logarithmic functions; 3, to be able to graph a logarithmic function that is undergoing transformations; and 4, to be able to find the equation of a logarithmic function when given the graph of that function. So recall from our last lesson that the basic form of a logarithmic function is y equals log cx. And in English, the question was, what exponent, y, do I give to my base c to get my answer, which is x? So for example, if we had a question like log 216, the answer to that question would be 4. I give the base 2 an exponent of 4 to get 16. So we get 2 to the 4th power equals 16. So the general form of a logarithmic equation that undergoes transformations now becomes this: y equals a log c b x minus h plus k. And we've seen all these letters before: the a's, the b's, the h's, and the k's. So let's do a little bit of a reminder to see how these variables actually change the basic function for anything, not just logarithms, but exponential functions, radical functions, quadratics, everything. So remember that a is your vertical compression or a stretch. And if it's negative, it means it's being reflected in the x-axis because your y values are changing. B is a horizontal compression or a stretch, and a reflection in the y-axis if it happens to be negative. And remember that if this is a whole number like 2, then all your y values are shrunk by a factor of a half. Sorry, all your x values are shrunk by a factor of a half. H is your horizontal translation, so how far it moves right or left. If it's positive, it moves to the left, where if this number is negative, it moves to the right. And finally, k is your vertical translation. If k is positive, the whole function is moving up, and if k is negative, the whole function is moving down. So here's an example for you. It says, use transformations to graph the following logarithmic function. And the function is y equals 2 log 3, in brackets, negative x plus 1 minus 3. And then we're going to identify the following characteristics: the equation of the asymptote, the domain and the range, the y-intercept if it exists, and the x-intercept if it exists. So the first thing you need to do is remember that we need inside these brackets a positive x value. So we're going to rewrite this right off the bat by removing a greatest common factor of negative 1. And that now becomes x minus 1 and then minus 3. So remember what we also decided in class is that the easiest way to graph this thing is to find the normal points for a log 3x function. So we're going to take a look at it in terms of log 3x. And then we're going to apply the transformations to those points. So if I put in a value of, say, an x value of 1, that means that I'm finding log 3, 1. So what exponent do I give 3 to get a 1? Well, that answer is 0. The next number I would choose is probably 3. So what exponent do I give 3 to get 3? And that is a 1. My next x value is going to be 6. No, it's not. It's going to be 9. Because what exponent do I give 3 to get 9? And that answer is 2. And my final x value would then be 27. Because what exponent do I give 3 to get 27? And the answer there is 3. So what we can do now is apply the transformations to these points. Remember that we like to do reflections and stretches first. So in terms of the x values, there is a negative in front of here, which means all your x values become negative. So instead of a 1, we get negative 1. Instead of a 3, we get negative 3. Instead of a 9, we get negative 9. Instead of 27, we get negative 27. In terms of stretches or reflections for our y value, this 2 affects the stretches and reflections, so we need to multiply every number by 2. So we've now taken care of the negative, and we've taken care of the 2. We need to take care now of the translations, so the moving of left and right and up and down. So after we do that, we will have our new points. So we've got an x value of, well, when it says x minus 1 inside the brackets, that means it's moving 1 unit to the right. So we need to add 1 to each of these numbers. So negative 1 becomes 0. Negative 3 becomes negative 2. Negative 9 becomes negative 8. And negative 27 becomes negative 26. This negative 3 at the end of the function means that every point moves down 3. So 0 becomes negative 3. 2 becomes negative 1. 4 becomes negative, or positive 1, sorry. And 6 becomes 3. So now we can plot these points on a graph. Now I already put the graph in here. I've changed the x-axis because I know I need to go as high as negative 26. So I'm going to plot these points. 0, negative 3 is 1 point. Negative 2, negative 1 is another point. Negative 8, positive 1 is another point. And negative 26, positive 3 is our final point. So we can draw a smoothish curve through all this stuff. Not bad, I guess. And there is our logarithmic function. So let's find the following characteristics. The equation of the asymptote. Well, the asymptote normally for a logarithmic function is at x equals 0. This graph has been shifted over 1 unit, so that means our equation of our asymptote is just going to be x equals 1. That's why my graph is going close to 1, but I guess it's kind of crossed over because this is 1 right here. So x equals 1 is our asymptote. Domain and the range. Well, the range, these logarithmic functions go on forever up and down. So our range is y is all the real numbers. But our domain, it goes everywhere to the left of positive 1. So our domain is x is less than 1. Now it can't equal 1 because 1 is a asymptote. Our y-intercept, if it exists, well, we found it. Our y-intercept happens to be at negative 3. So our y-intercept is at 0, negative 3. And our x-intercept, if that exists, our x-intercept can be found. We've put it somewhere between negative 4 and negative 6. So we can just estimate that as saying approximately negative 5, 0. So our final example says, your turn. The red graph can be generated by stretching and reflecting the graph of y equals log 4x. So y equals log 4x is our blue function here. Write the equation that describes the red graph then. Well, it says it's going to be stretched and reflected. So by looking at the two graphs, I can see that it's obviously been reflected. It's been reflected in the x-axis. So automatically I know that means that it's a negative log 4x graph, because it's been flipped. All the y values have been flipped. Now I need to compare this point here to this point here. So normally it looks like on a normal log 4x, it has a height of 1. Now this one has a height of negative 3. So it means that this value, you go from positive 1 to negative 3, that we multiply our y values by negative 3. So there's a negative, here's the 3, log 4x. So let's double check and make sure it hasn't been moved horizontally. Well, the y-axis still acts like a asymptote, so it hasn't been moved horizontally whatsoever. It hasn't been moved left or right, or else it would be crossing this y-axis if it was moved to the left, or a different line would be acting like a y-asymptote or a vertical asymptote. And it hasn't been stretched horizontally, or you would be able to see that as well. The graph would look a little squashed or spread out. So here is our function. So in summary, transformations affect the logarithmic functions the same way that they affect any other type of function. And the general form of a logarithmic function is y equals a log c b x minus h plus k. And remember that a, b, h, and k each have their own way that it affects a logarithmic function, or any function. As always, the easiest way to graph a logarithmic function is to find some main points on the basic function and then apply the transformations to those points. Then all you need to do is just plot those points. And finally, knowing the points that a basic function passes through will also allow you to construct the equation of a logarithmic function after it's been transformed. So if you're given a picture of a function, you need to know what the normal function looks like in order for you to find the equation of the new function. So your assignment is on pages 389 to 391. Good luck, and we'll see you in class.